our today's seminar, and today we have Francesco Sala from Pisa University or University of Pisa. I don't know how should I pronounce it. And the title is on the first page: Cohomological Hall algebras, their representations, and Nakajima operators. So please.
Thank you. So thank you for the invitation. And okay, so the goal of my talk is to give a brief overview of the theory of cohomological algebras and their representations, and discuss how Nakajima operators, Nakajima-type operators fits into this framework. And please stop me anytime you feel it. If there are questions on it, please go ahead.
Yeah, you can count on that. Yeah.
Okay. Okay. And so let me start by saying that, okay, the first part that I want to recall is, sorry, what is a cohomological algebra? And so what I will recall is simply cohomological algebras of surfaces, and that's it. So let me fix the notation. I will consider, we'll fix a smooth projective surface over C, and let the COHAs denote the moduli stack of coherent sheaves on S, and then R COHAs is my notation for a derived enhancement of COHAs.
What
Now,
do
as
you understand? So you wanted to interrupt you, so well, that's
yes.
I follow your suggestion. So what do you call derived enhancement?
It's simply an open substack of the derived stack of perfect complexes on S. And that is where you impose the condition that the families are coherent. So they live in the standard art. Fiberwise.
Yeah, but do you consider it whatever infinity stack, DG stack?
Yeah, exactly. Yeah, in the setting of Luri, Toen, Vezzosi, and so on.
It's
Yes.
slightly different settings, but anyway. Okay, so it's not just a stack, it's stack with some additional structures. So, yeah,
Yes, but
like
then in what I will say in the following, so the terminology cohomological means that I will treat either Born-Moore homology or the Grothendieck group of coherent sheaves, or bounded direct categories. Now, when you consider Born-Moore homology or the Grothendieck group of coherent sheaves, they are insensitive of the derived structure. So there is no need to introduce this guy here. On the other hand, I will mention also the result in which that a result related to categorification of cohomological algebras in which the derived enhancement plays a role. But this will show up later on in the slides. So the slides should be.
and so just you will speak about two-dimensional versions
Yeah.
of cohomological
Y-
Hall algebras only.
Yes. As
Oh.
usual, when I give you a talk in front of you, I apologize that I do only
You
2D.
don't have to apologize because I know what's a more general theory, but just
Yes.
for graduate students, which I see
Yes.
some of them. Yeah. Okay, good.
So
So
I
it's two
always,
di
yes, it's only two-dimensional. I always sit
okay.
myself to 2D.
Okay.
And
And it's always
so,
will be projective. Your surface will be projective.
no, will be relaxed later on.
Okay.
So
Okay. Mm-hmm.
it's only that my life is easier if I impose as a projective. And in this part, also in the part of representation, I will say it is projected in order to make the talk easier yes, for me. Okay, so this is I fix S, it's a smooth projective surface, and then I fix this stack. And now, as usual, in the business of all algebras, the way that you define the algebra structure is via a so-called convolution diagram. So let me recall what is this convolution diagram. And so the convolution diagram is a diagram where on the left-hand side, you have two copies of the original stack. And on the right-hand side, you have, again, your original stack of coherent sheaves. And then in the middle, there is the stack of extensions. So the stack of short stack sequences are these four. And then you have two maps, evaluation EV2, I call EV2, and then EV1 times EV3, in which the first one sends a short stack sequence to the middle term, and then this one sends a short exact sequence to the extreme elements in the short exact sequence. Okay, and then let me recall that from the point of view of the properties of these maps are the map EV2 is proper, representable as a map of stacks, and then EV1 times EV3 is the rival CI. So this is a notion that if you are not aware of it, simply means that the cotangent complex of this map is perfect of amplitude -1 and 1. Sorry, but what it really is needed here is the fact that thanks to these two properties, indeed we have that there is a proper push forward with respect to this proper map, and then there is a pullback with respect to this map. So this is what should remain if you are not aware. It's the first time that you see this notion on the rival CI. Okay,
Now,
and
if I drop the condition that S is projective, do I still have both properties, or there will be
yes,
problem with properness? No.
but you need to impose that this is properly supported.
Okay, all right. Mm-hmm.
Otherwise, yes, otherwise you have a problem. Okay, and okay, so this is a theorem due to Caprano and Vassero and Yu Zhao for zero-dimensional sheaves that they say that, as you will see in a second on the screen, he says that the Borel homology of the stack of coherent sheaves on S as the structure on associative algebra, and the product is indeed given up to the box product as a pullback and a push forward with respect to the maps that I showed you before. So now in a second, I will return back to the diagram again. Sorry, let me close with something that makes this sound. Okay, so in a second, I will go back to the diagram again. And so what is the point here is, again, the convolution diagram, the maps has the right properties, and so you can define this multiplication. Now, as you may see, going back to the diagram, what you do is really, you go from the left-hand side to the right-hand side by pullback and push forward. And in the notation in the slide, there is an upper shriek simply because you are working at the level of Borel homology. And so this is the right pullback, let's say, that one has to consider. And this gives rise to what is called the cohomological algebra of the surface S. Now you may replace the Borel homology with, for example, with the G0, which is the Grothendieck group of coherent sheaves on the stack. And then the same machinery works, and you have indeed K-theoretical algebra. And to be honest, the way that these people proved the theorem was not via derived algebraic geometry, but they used some perfect obstruction theory in order to show that indeed this upper sheik exists. This is the difficult part. One of the difficult part of the theorem is proving that this upper sheik exists, and the other one is proving the associativity.
Yeah,
And finally,
let me ask you sort of information question. In that paper with Maxim in 2010, I guess, where we introduced this cohomological Hall algebras, we indicated that it should exist as an object in the appropriate category of motifs, like in the category of Voivodsky motive, then any realization, including periodic cyclic homology or taking K0 or whatever, should give you a kind of realization of that. Is it proven by someone or not?
you mean at the level of motives?
Yeah, at the level of motives, because
No,
obviously the constructions are motivic, so it's a question about proofs.
I agree, and I don't think that I know that maybe some people maybe are working on it in the sense that I know that there was I noticed in the list of people that gave talks in this seminar before that, for example, there was Victoria Hoskins, and so they are working. I believe
Yeah,
that they.
but it's very, 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 very special story. I mean, yeah, of course, she works on on motives, but not on the structure of the
No,
algebra.
yes, but then this is the only I mean, this yes. I mean, yes, this is the
Yeah.
answer. So the only person
Okay.
that I know that is interested in models is Victoria and Simone, and it would be natural to go to models because since they already, I mean, develop a lot of the techniques there. But I don't think that no one at the moment actively is working on it.
Mm-hmm. Okay. Okay.
And also what I'm going to say now, okay, so now I will make a comment about your 3D case. So here, for example, what Maura and I proved some time ago is that you can categorify. So this means that at the level of the bounded derived category, here of the real derived stack, so you have a monoidal stable infinity category, so that this is seen as a stable infinity category as a monoidal structure. And this monoidal structure as again as a tensor underlying tensor product is given by the usual pullback and push forward, but now at the level of bounded derived categories. And the important thing for us was that we noticed that indeed the stack ARCO of S has a deeper structure. It's a so-called two-signal space. Or in other terms, it's already an algebra in correspondence systems. And then what we did was simply apply some realization factor in order to translate being an algebra in correspondence to being an algebra in stable infinite category. So I believe that if you can do something similar in 3D, for example, you can apply all the realization functions that you like, and then you get a lot of different categorical algebras or honest associative algebras.
Yeah, and there are some properties, maybe not problems, not
Yes.
technically minor with the potential, but from the kind of far distance. Yeah, you're right. I have a kind of a question. You see, you take, okay, like abelian category, coherent sheaves, and then you take the stack, and then some maybe
Mhm.
derived extent. And when you
Mhm.
take db-coh, you take it's db-coh of this stack or whatever its extension. Now,
Mhm.
do you know anyone who defined COHA without singling out a particular T structure in the derived category of coherent sheaves?
So you mean
Well,
by taking another one? By
by
taking
taking whatever, I mean, I can give many suggestions, but my question is that
So
so
this is a
far,
part,
yeah,
yes, this is part of a paper that I will cite later on with Diaconesco in Porta. And so a priori you can replace so you can replace Arco of S with any first you don't need the proper you don't need that the surface is proper, so you need only properly supported, let's say. And then you need a T structure that has the property of being open, which is equivalent to say that the corresponding stack of flat family with respect to this T structure, the moduli stack parametrizing flat families of coherent sheaves but coherent with respect to this T structure is open in the moduli stack of pseudo-perfect complexes or
yeah,
properly
yeah,
supported.
yeah. But you need to choose a T structure. So that's
I needed
actually
to choose, unfortunately, I needed to choose, yes, I needed always to choose a T
yeah,
structure.
yeah, yeah, yeah. Okay, so you're not alone in this company. Yeah. Okay, good. So then,
Also,
yeah.
yes, let me add one other, yeah, I mean, I don't know if I will cover everything that I prepare, but okay. So
Yeah, well,
let
it's
me,
interactive talk, so
yeah,
yeah.
it's exactly. So it's no problem. So let me say another thing. So a priori, one can wonder if you need the entire stack of perfect complexes, or it would be enough to take the entire stack of perfect complexes, and then consider some cohomology or some other cohomological theory. But it's not clear because already one of the problems of all algebras is that all algebras only realize half, right? Half of the existing quantum groups. And then if you want to So double it, either you double in algebraic way by using Grimfeld double, or you want to double it inside a representation. Now that this is the usual story at the level of Nakajima varieties. You have some cohomological algebra for quivers, then the two-dimensional cohomological algebra quiver that acts on cohomology Nakajima variety, and then as a subalgebra on the endomorphism of the cohomology Nakajima variety, then you double it, no? But doubling, since, as I will explain later on, that you need only two T structure. You need, you need a T structure and a torsion pair. And so at the end of the day, you need only an original T structure and then the tilted with respect to this torsion pair. This would be enough to get the whole quantum group somehow.
Yeah.
So this is what I will explain also later on.
This story I understand. The thing is that the usual constructible Hall algebra, which is defined in a similar way by the same correspondence, but for the different realization, like you take motivic constructible sheaves, it exists in the derived version due to Toen, and then I think he did over finite field, and we later did with Maxim over a field of characteristic zero, but it's derived. You start with a triangulated category, no particular T structure. So I do not know an analog of this for cohomological Hall algebra. So that's what was my question. But since your construction depends on the T structure, I assume that you don't know it either. Okay.
No,
good.
because and also if in the case if I wanted to get instead of getting half by using an whole algebra, it seems to me that I need only to consider two different arts instead of one in order to get all. So from this point of view, from the point of view of constructing quantum groups, it seems to me that the formalism is just enough somehow.
Okay.
I don't know. This is my selling point somehow. But yeah, okay. But we can discuss this. I'm not aware of the paper that you're mentioning, so maybe you can tell me more later. Okay, so now this was it was supposed to be a brief introduction to what cohomological algebra is, and also this theoretical and categorifiable algebra. And now let me say again what was asked before. So the first thing is that everything works outside the level of quasi-projected surfaces. It's enough that one replace the coordinate sheaves with properly supported the coordinate sheaves. And mostly because, because for example, you wanted that the map, the projection to the middle term, the projection for the shortest sequence to the middle map, it's to the middle term is still projective, and so you need some properly supported condition. And then the other thing is that there are also equivariant versions of the theorems above in which you act by a torus, and then everything is equivalent with respect to the torus. And finally, let me say that this categorification that I described, this is really sensitive of the derived structure in the sense that, as I said before, Bohr-Moore homology and G0 do not fill the derived structure. They are insensitive, but the bounded derived category is sensitive. And so these two things are not the same. And at the moment, no one has has provided a construction of this categorified Hall algebra that works exactly at this level. So for a categorification, you really need the derived algebraic geometry. But for the rest of the talk, you can completely forget about the categorification and maybe think only about Bohr-Moore and the G theory. So indeed, most of the construction, the result I will discuss, they work just fine in all three cases. And so I will denote the theory simply by H. And then when a result is valid only in Bohr-Moore or only in K theory, then I will specify. And similarly, instead of recalling cohomological algebra, theoretical algebra, and categorifiable algebra, I will simply denote all algebra in this way. Because again, some of the constructions works just fine for these three theories. And now the question that I want to address today, and I already know that I will not be successful in addressing completely, is the following. So one of the central goals in the theory of cohomological algebras is to describe explicitly these cohomological algebras by generators and relations. and in a way to understand if they realize, for example, already known quantum groups, or they are used in order to introduce new ones that were not present in the literature or in representation theory. And so from this point of view, this central goal, as I wrote, central goal in the theory of COHA was achieved for, I call it the smaller COHA, which means some cohomological algebra associated with subcategories of the abelian category of coherent sheaves on S. So usually when there is no underline, it means the category. When there is underline, it means the corresponding stack. So again, when you consider some smaller cohomological algebras, so cohomological algebras associated with the sign subcategories, then there is open, there are results that allow you to describe them explicitly by generators relations. And this is what I want to address now. I want to explain what is known in the literature and what's going on and what I'm doing. Yeah, so as a first thing, let me be precise here how I can construct the smaller COHAs. And so the way is as follows. So you need to fix a set subcategory of the abelian category of properly supported sheaves on S. And then you need also that the corresponding moduli stack of objects, of a flat family of objects in this category T is open. And then thanks to these two properties are enough in order to get a cohomological algebra associated with T, a theoretical algebra associated with T, and a categorical algebra associated with T. So the first main example that I want to address is the category T is the category of zero-dimensional sheaves on S, and the corresponding stack that I denote by R cos 0S is derived moduli stack of zero-dimensional sheaves on S. So in this case, since T is a set subcategory and this stack is open in the stack of all coherent sheaves, is open and closed. Then we get that in this case there exist all the algebras that I mentioned before, but also we have a complete understanding of the algebraic structure of these algebras. And then when I say we have a complete understanding, it means that we have a description of them by generators and relations. And now I will state the main results for these COHAs. So again, the zero here that will appear also in the next slide means zero-dimensional. So these are COHAs of only zero-dimensional sheaves. And so first, let me mention that by notation, I will denote by the so-called spherical Hall algebra is simply the subalgebra generated by the Borel-Moore homology or the G theory of zero-dimensional sheaves of length 1. Only of those of length 1. Okay? And so this is the spherical part. And then there is a theorem by Schiff and Vassereau. So their first result is for C2 with the action of the torus C star times C star. And they say that the localized version, localization with respect to the torus C star times C star, the localized version of the spherical Hall algebra, the spherical cohomological algebra, is a positive part of the so-called affine Yangian of GL1 that I believe you had I noticed that you had a talk before about affine Yangians. And so this is the affine Yangian of GL1. So it was introduced in this talk by Jindal, if I pronounce correctly his surname. And then also they proved that the spherical parts gives everything, gives all the zero-dimensional, gives all the cohomological algebra zero-dimensional sheaves on C2. And then
when you say localized, you mean you tensor with rational function
yes,
on
exactly.
the weights, which are epsilon 1, epsilon 2. Okay.
Exactly, because I don't want to introduce any nilpotent variant, because thanks to the nilpotent variant, I can remove localization. I guess this was indeed addressed by the Jindal is the I'm pronouncing correctly. By
Jindal, more or less.
Yes,
correct.
and so and then the point here is that this is a positive part of the Yangian, and this affine Yangian is given by generator relation. There is an equivalent description in K-theory in which the Yangian is replaced by the elliptical algebra or equivalent by the quantum toroidal
Yeah,
GL1.
Francesca, this the right hand side say for the positive part of this covariant Yangian, it appears in our three-dimensional story with Rabchak, Yang, and Zhao, but on the
Yes.
left-hand side we have some three-dimensional equivariant spherical algebra, and probably it's not a problem to prove that our spherical algebra is just isomorphic to the left-hand side in your formula. So I believe that it's kind of obtained your first isomorphism. Yeah,
Yes.
it has a
Yes, so you have
three-dimensional upgrade.
you
Yeah,
have
okay.
you consider some toric Calabi yes, toric Calabi
In
triplet,
this
yes.
case, it's C cube.
Yeah.
It's just
Yeah.
C2 cross C. Okay.
You're saying that has a direct generalization for the three-dimensional version? I mean,
Yeah,
Yeah, yeah.
Okay.
In this.
But this is what address there are yeah, you have different papers about this, no? Because there is one paper in which you define, you studied from the point of view, so you studied your 3D COHAs for the resolved conifold, for C3 and so on. And then also you have an action of the affine Yangian of this moduli space of spike instantons of Nekrasov, right?
Yeah, I
So
think that
you
in that one we
yes,
proved this 3D analog, yeah. But then
yes.
later, Dylan Batson, he developed very general theory
Yes,
for
I'm aware.
arbitrary
But
local Calabi-Yaos, yeah. Okay.
But his theory depends on a threefold and then a divisor inside it, right? So something, yeah.
Yeah.
Yes, because, yes. Okay. Maybe there is another question.
Maybe a tiny question is in that case for the three-dimensional, we're still talking about the two torus, or is it the full general of a C star 3?
In 3D, so let me answer. In 2D, it's obviously C star cross C star. In 3D, when you have C cube, it's a product of three copies of C star, but the weights are related by one condition, that the product of epsilon 1, epsilon 2, and epsilon 3, which is a weight for the third torus, is equal to 1.
Yeah,
It's
yeah,
a Calabi-Yau condition preserving the top degree form. Yeah. Okay.
Yeah, that just wanted to confirm. Thank you.
Okay, so I hope that I will have more than 1 hour to finish my talk, but okay. Let's see. So now,
Yeah, you will.
okay, great. So the second result that I want to mention is more recent, and in cohomology is due to Melit, Minetz, Schiff, and Vasserot. And so what they have is the following. So let me show this part of the slide. And so they say, okay, you take any smooth surface with the pure cohomology. And so they prove that, again, it's enough to study the spherically generated part, so the spherical subalgebra. And also, the spherical subalgebra can be given by generators relations. Now, in their paper, they use this notation of W plus. So they introduce an algebra W because as the affine Yangian of GL1 is a deformation of W1 plus infinity, where W1 plus infinity is some universal central extension of operators on the torus C star. Then at in the same footing, they introduce this WS, so some WS that depends on the cohomology of S. And then the relations resemble deeply the relations in the affine Yangian on GL1. And then they also prove that if I remember well, if, for example, S is a K-free surface, then this is a universal enveloping algebra or some Lie algebra. Okay. So the important point here, and the only point I want to make, is this is given explicitly. So there are generators relations. This is the main point that I'm trying to make here. And so then also they have some statements for the equivariant version with respect to a torus acting on the smooth surface. And their result and their techniques is that heavily depends on Negutz. So what Negutz did was he provided a description of the spherical theoretical algebra of zero-dimensional sheaves by generators relations. In this case, again, the relations really resemble those of the elliptical algebra. So what should remain of these first 30 minutes? It should remain that a priori, it's very challenging to describe the whole cohomological algebra of a smooth surface. And then what was achieved by these people was to provide a full description when instead of taking the whole COHA associated with all coordinates on the surface, they restrict to only zero-dimensional one. And then how they achieve this, how they prove this theorem. So how they prove this isomorphism and so on. So this is what I want to address now. So the way that they do it is that they need to proceed as follows. They first study representations of either the cohomological algebra of zero-dimensional sheaves on S or the theoretical algebra of coordinate sheaves on S, or zero-dimensional coordinate sheaves on S. And then you need to use Nakajima-type operators to determine the relations. So this is one approach. This is the approach that they follow, and this is what I want to address now. So now I want to describe a way to construct the representations. So now, everything that, all this, the representation that I will construct and so on, and we will see again over and over this convolution diagram. So the convolution diagram that I showed you before will appear again and again. And so now, in order to make my life really easy, so I will assume that the surface is projective. And then I will fix a torsion pair for the abelian category of sheaves on S. So let me remind you that a torsion pair is a pair formed by two subcategories T and F, for which there are no ohms from objects in T to objects in F, and any object can be decomposed in this way. So torsion pairs obviously generalize the notions of torsion sheaves and then torsion-free sheaves. And then, as before, what I would like to impose is that T is a series subcategory, so the torsion part is a series subcategory, and both the moduli stack of torsion objects and the moduli stack of torsion-free sheaves are open. And so thanks to these first two conditions, I already know that there exists a cohomological algebra, a theoretical algebra associated with the torsion part of the torsion pair, as I explained before. And then I fix a moduli stack, a stack inside the stack of torsion-free sheaves on S. And now the goal is to define left and right actions, a left and right action for the cohomological algebra associated with T on either the Borel-Moore homology or G0 of this moduli stack M. Now, so let me start by saying how we can define the right action. So as I said before, in order to define the right action, I will use again the convolution diagram that you saw before. And so in order to make the notation easier, I will denote by X the stack of torsion sheaves. And so what you would like to do is, okay, so this is the convolution diagram that I showed you before. And now what you would like to do is, in order to define an action, a right action of the cohomological algebra of T on the Borel-Moore homology of M, or the G theory of M, then you need to go from the left. So you need to pull back and then push forward. And so this is summarized in this line saying that if there exists exactly this composition, then obviously HM is a right HAT module.
Yeah, maybe for graduate students, I mean, there is a notion of a modification of coherent sheaf. I mean, this derived language,
this is I will address later on.
Yeah, okay. Yeah, it's just modification. There is a more general construction, actually, it's in my paper, I think 2014, which works for any, actually, it's, I would say it's derived. For derived category, it works for framed stable. The torsion pairs give you an example. I think I consider it in that paper. Yeah, so it's sort of a standard. If you ignore derived structure, so it's pretty
Yeah. I mean, here it's irrelevant. I
simple.
put the right structure simply because I copy and paste what I wrote before, and because applies also to the category file level. But if you don't care, you can remove this and work with the classical stacks. Yes. At this point, the only thing that matters is exactly that we can.
Can I quickly interrupt? So in this top correspondence, you have a torsion and the torsion-free part.
Yes.
Can you explain to graduate students what is the extension here?
Yes, thanks. I forgot to say this. Yes, thank you. Thank you so much. I forgot because this is important. So by this notation, I mean simply that I take a short extra sequence as before. So the short extra sequence before was 0, E1, E2, E3, 0, E3 is 0. And then I'm imposing that the E1 is torsion free, E2 is torsion free, and E3 is torsion. So here means the first factor E1 is torsion free, the second factor is torsion free, and the third one is torsion. Thanks. This is it's important because
okay, thank you. Yeah, that
later on.
explains
Thank
very
you.
well.
So and then again, so here here this is the op, no? So I will call RM this condition. If you can go from the left to the right, then I mean you will have a map. If you go from the left to the right, you will have a map, and you can define this right module structure. Now, similarly, in order to define the left module structure, the only thing that I have to do is reverse the order here, change what are the maps. And then again, what I need is going to the left, to the right, from the left to the right, in order to define a left structure. So again, in this case, I need to pull back with respect to this map, and then push forward to respect to this. So
But
if I have this...
They do not commute, as far as I understand.
No.
No. You don't have a bimodule.
No, this is very important. And it's very... No. And this is very important. Thanks. Yes, I don't have it. And yes, and it's fine with me. And now the point here is, okay, so a priori I have some condition that say if there exists, if this is well defined, this is a tautology. If this is well defined, then I have a left module structure. And then if the other one is, if this one is left, it's well defined, then I have a right module structure. Now, one hopes to have some conditions in order to verify that these LM and LN RM are satisfied. And so first, let me mention that, as Jan was pointing out, this is not a bimodule. And now let me say how you can check really by hand if you can realize a right module or a left module. And so in order to realize a right module, what you need is that your stack is open. For example, your classical stack is open in the stack of torsion-free sheaves. And also you need to realize that if you take a shortest sequence where the last term E3 is torsion, and the second term, the term in the middle is in M2 in M, then also the kernel must be in M. So anytime you have a shortest sequence where you fix the middle term and the last term on the right, and a priori here you have the freedom to take all possible coherent sheaves, then what is saying this is that no, you don't have any freedom. You must have that this is also in M. And so this is called the right take pattern. This will be called the right take pattern because we will induce a right action. And then the left is the one that says that if you have an extension between an object here, and then a priori you don't know what you have here. A priori you can have a coherent sheaf. Then you must have in the middle also M, something that is torsion free. And this is the left take pattern property, and this must be open. And then this is two side means that you have the freedom to take everything in the middle of everything in the left, and then always you get a shortest sequence where the first and the second term E1, E2 are in M, and then the torsion part is always in E3, in X. The torsion, yes, and E3 is always torsion. Sorry. Now, I assume that, it would be almost impossible to memorize right now this condition. if it's the first time that you see them. But the point is that these conditions, what are conditions that you can check in examples, and they allow you to construct the following. If you have a left or right Ecke pattern, then you have indeed HM will be a left module or a right module. And if M is a two-side Ecke pattern, then you will have both a right and a left module structure, and it will not be a bimodule structure. And so what we are looking for now are what are examples of two-sided Ecke patterns, because we like to have left and right modules. So let me go back one sec again and summarize. So let me summarize, at least for the right action. So what should remain from this story is the following, is that thanks to the convolution diagram, the usual convolution diagram, you can always define module structures for a smaller cohomological algebra associated with the torsion part of a torsion pair. And these are module structure over the Borel-Moore homology of the modular stack of the torsion-free part. And in order to construct explicitly the representation, then you use the usual convolution diagram in a suitable way. And then in order to verify that indeed you get this right and also the left module structure, you have some conditions, this is called the left and Ecke pattern, that you can verify in practice. And in the following, I will give examples. So don't worry, this will return, so I will give you examples. But now let me say the first case in which this can be used. And the first case is indeed the zero-dimensional sheaves. So if you take zero-dimensional sheaves, then the category of zero-dimensional sheaves is the torsion part of a torsion pair. And so this is my X. And then you have nice examples of two-sided Ecke patterns. So what are these nice examples? For example, one example is the Hilbert stack of points on S, which is simply the Hilbert scheme of points on S times BC star. This is a first example. So one in practice can check the condition that this is a two-sided Ecke pattern for zero-dimensional sheaves. And this is what was mentioned by Jan before, that these left and right action resemble action by modifications. And indeed, the stack of extensions that I wrote before is a stack of modification of object in M by object in X. And then the second example, these were both, the second was addressed deeply by Negutz, is the case in which you have the moduli stack of Giesecke stable sheaves on a smooth projected surface satisfying certain conditions with the fixed rank and the fixed chain class, and you want that the rank and the product between the C1 and the ample divisor is coprime, because you want that stability is equivalent to semi-stability. And so this was studied, this example was deeply studied by Negutz. And so in these cases, the fact that I have two-sided Ecke pattern means that the cohomological algebra of zero-dimensional sheaves on S acts on the left, on the right, on the Borel-Moore homology of this stack. It acts on the left, on the right, on the Borel-Moore homology of this stack. Okay. And now, since you have this, how you determine the algebraic structures? So now you must proceed in the following two steps. So the first step is that you work at the level of this left and right module. And the second one that I will explain now how to do it is that you consider Nakajima-type operators. And so again, the approach followed by these people is that instead of obtaining an intrinsic description of the cohomological algebra of zero-dimensional sheaves on S, they work at the level of this left and right module. For example, the left and right module given by the Borel-Moore homology of the Hilbert stack of points on S. And then there you define Nakajima-type operators. Okay, so let's see what are these Nakajima-type operators. So let me remind you that, so if you take the stack of of zero-dimensional sheaves that are on length 1. So these are the sheaves are supported at one point, and so by varying of the point you get all S. But then you have to remember the stack structure, and so the classical stack of zero-dimensional sheaves on S of length 1 is simply S times BC star, and then the derived one is a derived enhancement of S that is irrelevant for this discussion times again BC star. And now one important thing is that the Hilbert scheme of points, we can restrict to the Hilbert scheme of point. This is a fine moduli space, and so there is an universal sheaf. And now I can, in order to define Nakajima operators, I can restrict a lot my convolution diagram. So this is the same as before. But now, as you may see, I restrict here, I take a moduli space. Here I take the surface. Here again, I take the moduli space. So I'm restricting myself a lot. But thanks to this, what I get that is very important is that I realize my stack of extensions, the stack of extension that is needed in order to define the left and the right action, is a projectivization of some complex. This is a projectivization. And then the Nakajima operators here, those that were mentioned by Jan before, this is simply given again by pull back and push forward. So you have again pull back and push forward, and then this is since you have the action of the C star, I can take characters with respect to this action, and these are denoted in this way. So in K theory would be the trivial line bundle with the C star equivariant structure given by this character, and in Borel homology would be the Fertian class of such a line bundle. And so you define this operator ED and FD. So this is more or less very similar to what Nakajima did 30 years ago, but Nakajima didn't have this part. And so he was simply considering at this level only tensoring by coupling in cohomology with the fundamental classes. So here we have more freedom, and so we get more interesting families operators. And now these operators, since I'm restricting to simply coherent sheaves, zero-dimensional sheaves with the length 1, they can be seen as an element of this spherical whole algebra. And then the key point here is that I restricted myself so much that the stack of extensions was a projectivization. And this is a great news, because indeed, by looking at the computation done by Negutz or by Melit, Minetz, Schiff, and Vasserot, this is the real important key point in order to express computer relations. Because then the pull back and push forward is simply collapsed to be some push forward of the tautological line bundle on this projectivization. And so you can really do computations. And then they did the computation, and then they determine all the relations. Okay, so what should remain all this? This should have been the first 30 minutes of the talk, but got longer. Should remain the following. In the case of zero-dimensional sheaves, so first you can define a cohomological algebra. Second, you can define an action of this cohomological algebra on the Borel-Moore homology of Hilbert schemes of points on S. This action somehow generalized the old action of Nakajima-Groznyovsky. And this action gives you, it's a left and right action. And so then you are able to define the operators that you see on the screen, and you are able to compute all these the relations between them. And this is everything very explicitly very down to earth when you restrict so much your setting that you can consider these very simple operators. And now, what can we say beyond the zero-dimensional case? So this is the new interesting part is the following. So instead of restricting myself to zero-dimensional sheaves, I can take all possible torsion sheaves, right? So if I take all possible torsion sheaves, I take torsion sheaves that have dimension also 1, and so on. And then the torsion-free part is really formed by torsion-free sheaves. So torsion sheaves and torsion-free sheaves obviously form a torsion pair. Moreover, torsion sheaves form a set subcategory, and both the stack of torsion sheaves and the stack of torsion free sheaves are open in the stack of coordinate sheaves. And so I have and also this is also closed. And so I have a cohomological algebra associated with all torsion sheaves. Now, having at disposal a cohomological algebra associated with all the torsion sheaves, one could ask, okay, can you provide a description by relations, by generators relations of this algebra? And how can you do that similarly to what these people, Neguz, Melit, Minetz, Schiffenwasserau did before? And then the answer is, yeah, let's see what we have in this case. So first, the first thing that I have to address is how I construct representations. And so I want again to construct a left and right representation, because only having at disposal a left and right representation, I can construct, I can define Nakajima operators that eventually are fundamental in order to compute the relations. Now, it's very sad, but unfortunately, most of the time, it's very difficult in this case to construct two-sided K patterns. And moreover, two-sided K patterns that are moduli spaces, I'm not aware of any of them at the moment. And so how we can circumvent this problem? So let's first try to construct an action of the whole algebra of the cohomological algebra of torsion sheaves on the Borel homology of the modular stack of all torsion-free sheaves. So we take as M all possible torsion-free sheaves. And then I wanted to mention the following. So if I take a shortest sequence where I have as the term E-free torsion, E-free torsion sheaves, and then in the middle I have a torsion-free, obviously a subsheaf of a torsion-free sheaf is torsion-free. And so this is again torsion-free. So this was the so-called right K pattern property. And so I have a right module. The Borel homology of this stack gives me a right module with respect to the algebra associated with this stack. On the other hand, if you take an extension between a torsion sheaf and a torsion-free sheaf, a priori no one tells you that this is torsion-free. Indeed, you can take the trivial extension and it will not be torsion-free because it's a direct sum where this appears. And so this is why I'm mentioning this, because in order to have also the left K pattern property, you must somehow find a way that anytime you take an extension by a torsion and a torsion-free, you get in the middle torsion-free again. And this is not the case. And so what we can do? So we can do the following. So this is not a left K pattern property. And so one can rotate this shortest subsequence. What this means? I have a shortest subsequence, but this is also a triangle in bounded in the right category. And so I can rotate, and I can rotate in this way. And then this triangle becomes a shortest subsequence in the tilted art. So what I'm doing is, thanks to the torsion pair, I can define a new T structure, not more the standard one. And then the art of this T structure is given by all possible complexes that have a cohomology only concentrated in degree -1 and 0. In degree -1, the sheaf is torsion-free. In degree 0, the sheaf is torsion, and the other cohomology, in the other cohomology degree, the cohomologies vanish. And so again, it's a complex concentrated in only 2 degrees. And so H-1 of E is torsion-free and H0 of E is torsion. And this gives rise to a new abelian category. And moreover, in this new abelian category, the role of torsion-free and torsion is reversed. So up to a shift, torsion-free sheaves becomes torsion objects for this art, and torsion sheaves became torsion-free objects for this art. How can I use this? So now, in particular, what I have is I take again my shortest subsequence, the one before that I rotate. This is torsion. This was torsion, and this is torsion free shifted by one. But torsion free shifted by one, they are torsion in the tilted arc. And any quotient of a torsion is torsion. And so this is again torsion in the tilted arc, and so is torsion free shifted by one. And so all of this to say that I don't have the left Ecke pattern property, but thanks to the rotation, I have a right Ecke pattern property in the tilted arc. And so in the tilted arc, I have a right Ecke pattern property. And I'm very happy about this because thanks to this right Ecke pattern property, given by the rotation and the fact that the torsion free up when you shift by one becomes torsion, and any quotient of a torsion is torsion, gives me a way to prove this theorem. And so although I don't have a two-sided Ecke pattern, I can anyway construct a left and right module structure for the cohomological algebra of torsion sheaves on S. So I have this module here. So the Borel-Moore homology of the moduli stack of torsion-free sheaves on S is a left and right module for the cohomological algebra of torsion sheaves on S. The G0 of the moduli stack of torsion-free sheaves on S is a left and right module for the K-theoretical algebra of torsion sheaves on S. So now I'm again more or less happy because I am again in the same situation as before. Okay, before here there was the Hilbert stack of points on S. Here there is this huge moduli stack of all torsion-free sheaves on S. But at least I have again a left and right module structure. And again, what should remain now is if you don't know how to construct the left module structure, the one way is to rotate, go to the tilted arc and construct there. Because when I am in the tilted arc, being a right Ecke pattern in the tilted arc implies having a left module structure. And so what about Nakajima-type operators in this case? So before, Nakajima-type operators were associated with the original surface. And what we did was that we restrict a lot the module because we consider only the stack of zero-dimensional sheaves of length 1. So also in this case, we cannot take all torsion sheaves and consider operators with respect to all torsion sheaves. A priori, yes, you can do that. But at the moment, I'm unable to compute relations for all of them. So we restrict to a smaller family of operators associated with the torsion sheaves. And so what is this smaller family? So we fix a divisor, and we fix also we fix an effective divisor in S. We fix an ample divisor in S, and we take alpha, and then for the moment I consider the category of torsion sheaves that are Simpson H semi-stable of the fixed slope alpha, where the Simpson semi-stability for torsion sheaves this would be one-dimensional torsion sheaves is given by this formula. Okay. And inside this abelian category, I will consider only those subcategories that satisfy these conditions. At the moment, they could seem like artificial conditions, but then these will be the useful ones. And so I will say that a subcategory of the category of Simpson stable sheaves, one-dimensional sheaves of slope alpha is admissible if any torsion sheaf is skin theoretically supported on D. And then we have also this condition on the maximal and minimal slope. And then we need to assume that the corresponding exists a corresponding moduli stack, and this is open and closed in the stack all semi-stable sheaves of fixed slope alpha. So this stack here and this category here will replace the category of zero-dimensional sheaves of length 1. So this will be my smallest category for which I will construct Nakajima operators. And now I needed to tell you what is the module. And so in order to tell you what is the module, I have to define what is this M. And so this M is simply, you take the category of all vector bundles on S, and then you impose these two conditions with respect to, again, slope, Arden-Racine maximal slope and minimal slope. And then this M, this is an open substack. So this is open. Okay. And so this stack will replace the Ibe-Skinner points in the discussion before. And so the family of Nakajima operators will be associated with this admissible category that I showed you before. And then the module will arise from this M that are all vector bundles that satisfy these conditions with respect to D. Great. And so this is a two-sided pattern. And so I am happy. So this is not a moduli space or a nice moduli stack like before. But still, I have a two-sided pattern. And so as I can consider the left and the right action as before, given by same diagram as before. And so I can define Nakajima operators as before. And so Nakajima operators will be given as before by going in this direction and by going in this direction. And moreover, since I have an action of C star on the stack of torsion sheaves, I have also the composition. And again, in this case, you have ED and FD. And so now the Nakajima operators are defined exactly as before. What I changed was the stack X is a stack associated with an admissible category of torsion sheaves. And now the Hilbert scheme of points was replaced by a category by a stack of torsion-free sheaves satisfying some slope condition. But the operators are defined as were defined before. And now what is the real result here? The real result, one of the results is the following. So we can use techniques from all algebras, also techniques from the approach followed by Negutz and Yuzao to prove the following. So we can compute effectively the relations for these Nakajima operators in this setting. And so, for example, let's take this geometric setting. I take a relatively minimal smooth projectility surface which emits a section. And I assume that the projection emits a unique singular fiber such that the underlying reduced scheme is an affine AD configuration of -2 rational curves. And I assume that there are at least 3 of these -2 rational curves. I assume that there is a torus. The torus could be trivial. And then I take as my admissible category simply the category that collapses to be formed by OP. These are all P1s, so OP1 -1 by varying of all the reducible components of the underlying reduced divisor D. So this is one can prove that these are Simpson stable of slope 0. And so I define Nakajima operators that modifies a sheaf exactly by using these line bundles over P1. And then what I get is the following. So what I get is that the action of these Nakajima-type operators on the Borel-Moore homology, equivalent Borel-Moore homology of M gives rise to an action of the affine Yangian of type AD in Borel-Moore homology. And if we go in K-theory, an action of these Nakajima-type operators on the equivalent G0 theory of M gives rise to an action of the quantum toroidal algebra of type AD. And so again, here what I'm doing is, before in the zero-dimensional case, Nakajima operators were modification of points by skyscraper sheaves, because these are length 1 sheaves or dimension 0. Here I modify my sheaves by using line bundles over P1s. And in this case, what I get is in Borel-Moore homology, affine Yangian type AD, and in K-theory, quantum toroidal algebra type AD. And maybe for those of you that remember and recall a very old paper by Ginsburg, Caprano, and Vasserot that is called Langland's duality for algebraic surfaces, they use similar operators to construct an action of the quantum toroid algebra of type ADE on functions on some moduli stack of vector bundles satisfying some constraints. And so this is a cohomological theoretical version of the result given by Ecke modifications associated with exactly these torsion sheaves that are pushed forward or line bundles from the reducible components. And we can also consider the case in which D is a smooth projective curve of genus greater or equal than 1, and D square is less than 0. In this case, we are in the process of computer relations. And so this will give some indication of the cohomological algebra of sheaves supported on curves of genus greater or equal than 1. What was before was an indication for a cohomological algebra associated with torsion sheaves supported on chains of P1. This would be the higher genus case. And this is what everything that I wanted to say.
Okay, thank you very much. So kind of one thing which a bit confuses me, when you have you're concentrated on the description of COHA in terms of generators and relations. Now, like for example, if you have a Kac-Moody algebra, there is no question about describing it by generators and relations, but there is a question about the class of interesting representations. And since you do not impose a stability condition, so what you get is just some representations of COHA in a huge cohomology space. So actually in my paper that 2014, 10 years old by now, in which the torsion pairs and all, actually there are many kind of you should really look at it, although it's outdated a bit. But the point was that one should look for stable framed representations, and then one gets a class of representations of COHA, which is in a sense interesting. It's like, there is this category O of Bernstein, Gelfand. So, and for example, in that paper with Mira, Yaping, and Gufang, we consider stable framed representations of COHA of torsion sheaves on three-dimensional Calabi-Yau on C-cube, and we recovered this generalized AGT conjecture. So I mean that it's a great and difficult problem you are trying to solve, describing the algebra in terms of generators and relations. But I think that there is equally interesting problem of describing interesting representations of
This is, our motivation was somehow a cohomological and theoretical version of this paper of Ginsburg, Caprano, and Vasserot. I don't know if you're aware of this very, very old paper where they first introduced this.
Yeah, of course I know. It's kind of mathematical attempt to understand a little bit this S duality. They modified. I mean, every whole algebra is a Hecke algebra, as you explained, and so this is why you call this Hecke pattern, because it's all Hecke. And
It's
so
all
then
Hecke.
when you construct modules by modifications, it's mimicking not only Ginsburg, Kapranov, Vasserot, but anyway, even story with arithmetic Hecke algebra, you modify. Okay, great. But since you mentioned like Yangians or whatever, like toroidal algebras, so an appropriate class of representations, it's something like highest weight.
Yeah.
And for that you need stability, and so that's what it's a remark. It's not really a
But the problem
question.
is the one of the thing that puzzle us as well. I mean, us means the trio, so Diaconescu, Port, and me, is that at the moment we are not able to really construct an action, a left. I mean, it will be enough to work with the right action and then go to the tilted art for some nice moduli space. When you consider this cohomological algebra of all torsion sheaves. So, for example, we have a construction of a representation of torsion of this cohomological algebra of torsion sheaves on a stable pairs on surfaces.
Yeah, yes.
But then we don't get both a left and right. We get only one of it. I don't remember if we get only a left or we get only a right.
Actually, it's an interesting, it's a kind of interesting question, but probably it will take us too far from there in relation to these Coulomb branches in 3D unequal force theories. They also, physicists think that they have a bimodule structure, but in fact, probably they don't. But anyway, yeah, I understand. I
So
understand.
in the paper, so when we did this construction here, so this construction here, so we also, one of the example that we did that was not derived completely from the theorem, but was derived by using same formalism, similar formula was for these stable pairs, Pandai-Thomas stable pairs on a surface. And we were also interested in the case in which you take Pandari-Thomas stable pairs on the cotangent of a curve, no? This corresponds to some
on the cotangent
Yes, so this corresponds to some
no, I
cyclicity
do not
condition
understand. On the cotangent of a surface, which
of the
is
curve.
of the curve, this I understand, yeah.
Okay, and then, but unfortunately, we get a left and right module only with respect to the action of co zero dimensional. When you take all torsion sheaves, then we get only a left action. I don't remember if it's left or right, but only one of it. So this was very sad for us somehow.
Yeah, maybe three-dimensional perspective will help, or maybe not. So your question is with coherent sheaves supported on curves, yeah?
Yeah, so the point is that we, at the moment,
which are
we say...
essentially Higgs bundles, yeah. Okay, yeah. And PT,
so let me add one thing. Already understanding for the COHAs sheaves, what is the corresponding stable framed module, it's open question as well. Because I completely agree with you that there should be some stable, some moduli stack of stable framed objects, for which the cohomology has a left and right action. But
I don't remember. I think Emmanuel has a paper with Donaghy and Pantyev where they proved an isomorphism of the moduli space of Pandari-Panda stable pairs on the threefold. I believe it's a product. In the simplest case, it's a product of the cotangent bundle to a curve with a line. So it's something three-dimensional. And moduli space of, well, stable or semi-stable Higgs bundles, which mean that exactly torsion, this coherent sheaves of pure dimension one.
yes, exactly. This one, for example. Yeah, this one. Yes.
So, but would it be helpful if you just, in this special case, just forget about coherent sheaves and work with Higgs bundles? I mean,
but what would be the right notion of a stable frame module for them? So what do you take as a stable frame? Because the frame means that somehow you are compactifying.
I understand. You have then to define the action.
And then a stable means for this.
It's interesting anyway.
So this is, no, I mean, Yeah, there are a lot of stuff that still has been needed to be done. I agree. So, and
Yeah.
here is the reason that I restricted to proper case, to the projective, the surface is projective, because otherwise, also when you are in the quasi-projective case, it's really complicated because you need to understand compactify. So this will be framed the notion, and then stability, but in this compactification, that should be related to the Ecke pattern property and so on. So this is for each bubbles, it's already
I
known.
understand. Yeah, we define. I remember years ago, I don't know, at least 10, we discussed with Emmanuel and actually maybe with my son the idea to use semi-orthogonal decompositions for constructing this kind of representation, but I don't remember what we ended up with. Probably nothing
Okay, I will ask him.
really useful. Yeah, but you can ask him. If he forgot, maybe I'll find some
No,
traces.
for me it would be great to have something smaller than this beast.
For
This
me
would
too.
be,
Yeah,
I
yeah.
mean, for me, the only reason to use, I mean, there were two reasons for using this. The first one was that this is a natural generalization of Gisburg-Kaplan-Vassero moduli stack. And the second one is that with this, we can really apply our formalism and so on, and then get some operators that we can compute the relations. This is, I mean, this is what we wanted. We wanted at least in this representation to see what kind of quantum groups arises.
Okay, yeah, all right. So maybe we should ask whether there are other questions by other people. Otherwise, it will be entirely private discussion. Okay.
Yeah, I'm very sorry. Yeah, very.
It's
Yeah,
definitely interesting to hear your question and your conversation. And it's
yeah,
very
but
enlightening.
I know that normally you have some questions. So Zongju,
Yes,
do
I
you
do.
have? Okay, then go ahead.
So I have two questions, and the first one was probably more general in the first part of the introduction. I mean, many of the settings, geometric settings, I'm not familiar with S being surface. I
Yes.
believe that most of the settings could be in the higher dimension. Am I understanding?
No, okay. No, I mean, the short answer would be no. The long answer is that when you already go to 3D,
Uh-huh.
so
So
when you
for
already go
example,
to
for this
3D, then
modular space,
okay.
doing
So
this
when you go to 3D, you have to use.
oh
So
yes,
first, you have to
definitely.
use the
When you
conservative.
talk about the torsion pairs, I can see that the torsion pair is much better to understand in dimension one because torsion is really torsion and frame really means free. But dimension two already makes
But this should
free
be.
not necessarily free.
You see, even in dimension two, there are so many difficult problems
Oh yeah.
that if you go to higher for 3 calabial, like if you take the total space of the canonical bundle on the surface, yeah, there is a theory of maximum. I mean, the more general theory of Coha, but you have to add the potential, the function on the moduli stack and look not just for the cohomology, but cohomology with coefficients in the sheaf of vanishing cycles. Now, for 4-dimensional, it's really interesting, but I'm not sure that there are too many papers on
So
that.
I mean in
But
order
let me
to
say
form
one
the
thing. Let me say one thing. I believe that most of this part about ocean pair, I believe that they can fit also in the. I believe that they can fit somehow in the 3D story of Jan. I believe because this was commenting before that although in his paper about representation of 3D coas, he didn't write in this language, it should fit there. This is my understanding of what he was commenting.
Yeah, it will give. Actually, I believe, I don't remember, maybe in that
Yeah.
paper 10 years
So,
ago, I considered
so the formalism, yes.
example of PT stable pairs in relation to. So I recall I wanted to interpret this Oblomkov Rasmussen Schende conjecture about algebraic knots in terms of representations of COHA for the T structure, which is a category of perverse coherent sheaves. I believe we did something of that with Emmanuel and Zheng Hua. Yeah, but in general, when you raise the dimension, everything becomes here kind of at least 10 times more difficult. Yeah. So then.
But the idea should be there.
The idea should be the same. I mean,
Oh,
you
this
should
answer
have
your
hacky theory in any dimension, but you know
Yeah.
how to do that. Yeah.
Because also the idea of Nakajima operators, this is also in their paper. So in their paper, I believe in the paper in communication and mathematical physics, they indeed studied the spherical part. And so it's again the same thing. So spherical in their sense means again generated by things that are supported, let's say 1 point, or maybe it was 1 vertex, no, because this is a quiver setting, most probably. But it's very similar. So I mean, all of this story propagates, it's always the same, but then there are some technical difficulties in order to make...
but again, Francesca, like PT stable pairs, it's just stable objects in the category of perverse coherent sheaves. So then you can generalize from this as well.
Yes.
Okay.
And I have a second question. So you given the torsion pair you did, and then you also have the twisted tilt torsion pair. This is for the representation theorists. They call it either is that the torsion or tilting pairs?
I'm not
tilt, you're probably not familiar. It looks like
no, I'm not familiar.
It's just the way I understand.
So wait,
torsion pair just shifted, but
yes, I understand. Where is this? Okay, now let me go fast in order to check it again. Yeah, I understand. I understand that. Yes, here. This is
I have a feeling
and I needed to use that because the point is that when you do modifications, modification usually you take when you do modification in order to define one action, the last term and the term that I call free, the first one on the right, it's always the one associated with the algebra. And then you want the other two to be associated with the module. And then if the one in the middle is torsion free, then you get again something torsion free as a subobject. No, this is automatic. So here the game is in the other way around. So you take as a first term in one on the left an element associated with the algebra. Then something in the middle is associated with the module, and then you want the quotient to be in the module. And this is done because when this is torsion, and so quotient of torsion is torsion. So this is what I use here, and that's it.
I see.
So this is the idea is transforming something that is torsion free after shifting by one is something that is torsion, because a quotient of a torsion shift is torsion, and this is the same idea. And but then this is a pattern in the tilted that gives rise to the left action in the original setting, because there is a shift. This is thanks to the fact that there is a shift and so on. So this helps a lot.
Yeah, I believe, if I remember correctly, the tilting or pairs, which says in the triangulated, if you put that in the triangulated category instead of using the Hom, using the x1.
Okay.
Under the x1, that becomes a tilting, it becomes a torsion pair.
Okay.
And they also talk about the that's called a co-torsion pair.
Okay. No, I'm not familiar with that.
Yeah, this is something just if you have this one, you could shift the one more time, and you get it using the extra one. This is very interesting. And for whole algebra, in the Lustics using the constructible construction, and which he gives a co-multiplication structure. So in the cohomological or K-theory, or did anybody?
So this is an announcement made 3 years ago by Davison and Kinjo. I don't know, since this is recorded, I don't know if, but I guess they also say it. Okay, so at the moment there is no coproduct available for two-dimensional cohomological algebras of surfaces. There is a coproduct available for A localized coproduct is available for 3D Kontsevich-Sorgenban COHA for quiver with potential.
Okay,
And
that's
then there is this work of Davison and Kinjo that they should provide a coproduct for a large class of 3D COHAs that should include also by dimension reduction the COHAs that I'm discussing now. But this was an announcement, and now there have been a lot of papers by Kinjo that are considered as an intermediate step in order to reach this final step. So it's expected, but there will be I don't know when the final step will appear.
Okay. Okay, well, thank you very much. I really appreciate your very inspiring talk.
Okay.
Thanks.
Other more questions? Well, if not, well, Francesco, thank you very much. Very interesting talk.
Thanks. Thanks.
Thank you. And so this
I'm happy
is
that
it.
you enjoyed it.
Yeah.